From the furthest reaches of our solar system, to the storms of Jupiter, to asteroid sample collection, NASA's New Frontiers program was created to tackle specific questions about our solar system, deemed top priorities by the planetary community. The first of these missions, New Horizons, launched in 2006, still provides groundbreaking scientific data today. New Horizons was humanity's first encounter with Pluto and its moons, uncovering that this dwarf planet is a dynamic world unlike anything ever imagined. But New Horizons didn't stop there. In 2019, this intrepid spacecraft visited the most distant object ever explored by humankind, named 2014 MU69, beginning the exploration of the mysterious Kuiper Belt, a region of primordial objects that holds keys to understanding the origins of our solar system. The second mission, Juno, has been unlocking Jupiter's secrets and sending us breathtaking images since 2016. By studying the planet's atmosphere, interior, and magnetic fields, Juno continues to improve our understanding of the solar system's beginnings, revealing the origin and evolution of Jupiter. Next up was OSIRIS-REx, a mission that arrived at near-Earth asteroid Bennu in 2018. OSIRIS-REx will directly sample an asteroid and return the sample back to Earth in 2023. The team will use state-of-the-art labs on Earth to analyze the sample, which will help scientists understand the possible building blocks of life, as well as improve our understanding of asteroids that could impact Earth. And today, we announce our next mission to explore our solar system.
NASA is pushing the boundaries of human knowledge and expanding the limits of technology. Today, I am proud to announce that our next New Frontiers mission, Dragonfly, will explore Saturn's largest moon, Titan. Dragonfly will be the first drone lander with the capability to fly over 100 miles through Titan's thick atmosphere. Titan is unlike any other place in our solar system, and the most comparable to early Earth. The instruments on board will help us investigate organic chemistry, evaluate habitability, and search for chemical signatures of past or even present life. This revolutionary mission would have been unthinkable just a few short years ago. A great nation does great things. We will launch Dragonfly to explore the frontiers of human knowledge for the benefit of all humanity.
Hello, welcome to NASA Science Live, your opportunity to go behind the scenes at your nation's space program. I'm Gray Hautaloma, and I'm your host for today's special edition. We've all just heard the great news that Dragonfly has been selected to visit Saturn's moon Titan, the next mission in our New Frontiers program. Now let's get a little context about that from our head of the Science Mission Directorate, Thomas Zurbuchen, and Dr. Lori Glaze, head of our Planetary Science Division.
Hey, I'm Thomas Zurbuchen, Associate Administrator for Science.
And I'm Lori Glaze. I'm the Director of Planetary Science Division at NASA.
And we're so excited to have selected Dragonfly to go forward as the next New Frontiers mission. It's the science that really motivates us to do this exciting and difficult mission, a mission that has elements of advanced instrumentation, but also has the ability of flying in that atmosphere of Titan, a world that we, of course, looked at with Cassini and Huygens, our international analysis with ESA and the Italian Space Agency.
And what really excites me about this mission is the fact that Titan has all of the key ingredients needed for life. Liquid water and liquid methane. We have the complex organic molecules, carbon-based molecules, and we have the energy that we know is required for life. And so we have on Titan the opportunity to observe the processes that were present on early Earth when life began to form, and possibly even conditions that may be able to harbor life today. We may be able to look for biosignatures there today. So what an exciting mission.
And of course, that mission is led by Principal Investigator Dr. Elizabeth Turtle at Johns Hopkins University Applied Physics Lab, but also by a core team that really brought together a very diverse group, close to 40% female, but also an engineering team that brought just a couple of years ago, brought together the Parker Solar Probe, a very hard technological, challenging mission, brought that together below cost and on schedule. So we're really excited to see what's going to happen here. Go Dragonfly.
Go Dragonfly.
Thanks, Thomas and Lori. They really wanted to be here with us, but they're on another continent right now. But we do have a lot of really interesting people with us today, and they're going to be able to answer your questions, so please send them to us. Use the hashtag AskNASA on Facebook and Twitter, or leave a comment in the box at whatever platform you're watching this on. Right now, I've got Kurt Niebuhr with me. He is the lead program scientist for New Frontiers, and he's going to tell us a little bit about why Titan is such a great place for us to visit. Welcome, Kurt. So let's get on right with that. Why do we want to go to Titan?
Thanks, Gray. You know, Titan is a really fascinating place. It's the only moon in our solar system that has a thick atmosphere. It's actually thicker than Earth's atmosphere. And it's a fascinating place because in this atmosphere, there are chemical reactions going on that actually cause organic molecules, very complex organic molecules, to be formed, and then they drift down out of the atmosphere to the surface, almost like a light snow that's always forming. And it's that kind of complicated organic synthesis that really drives our interest toward Titan.
As Thomas mentioned, we've been there before with the Huygens probe. What did that tell us?
The Huygens probe was provided by the European Space Agency, and it was a really tremendous mission. It was delivered by the Cassini spacecraft, and Huygens was the first probe to descend and land on Titan. And we're actually going to land Dragonfly near that location. And what Huygens did was tell us what the atmosphere is like, what kind of properties and conditions we can expect, and even to a limited extent what the surface was like. We would not be able to do the Dragonfly mission if Huygens had not provided the data that it provided.
It's kind of mind-blowing to think that we're going to the moon of another planet. The first time we've ever done something like that, landed and flying around like this. So tell us a little bit more, why is it such an interesting target for scientists?
Well, you know, in addition to that organic haze that's snowing down, Titan has what we call a methane cycle. You know, Earth has a hydrologic cycle where clouds form with water vapor and they eventually condense and it rains. Titan has something very similar to that, except instead of liquid water, it's liquid methane. Sort of like the liquefied natural gas that's in your propane tank for your barbecue grill. And this actually forms clouds in Titan's atmosphere, and it also comes together in storms, rainstorms, that then carve the surface and create lakes and rivers and canyons. And even though it's very cold on Titan, it has a lot of similarities to Earth in that respect.
Yeah, so it sounds like there are a lot of features on Titan like Earth, like rivers, lakes. So if we were with Dragonfly on the surface, I mean, would we recognize it, or is it like such an ancient Earth-like atmosphere we wouldn't know what we're looking at?
Oh, I think we would definitely recognize it. And one of the great things about Dragonfly is with the cameras that it has looking forward and downward, as Dragonfly is flying over the surface, it's going to be taking pictures and sending those back to Earth. So we will actually get the experience as if we were riding along with Dragonfly, looking down at this alien yet very familiar kind of surface that has these rivers and mountains. And I think that's going to be a tremendous experience for the public, and I think everybody's really going to enjoy it.
So this atmosphere, it's a lot thicker than Earth's, and that's really essential to what Dragonfly is going to do. So that contributes to the methane cycle and the snowing of organics. Tell us a little bit more about that whole process.
That is one of the most exciting things that the Cassini mission really revealed to us is how truly complex Titan is with that methane cycle, where you get the rain coming down, collecting into really large lakes like the size of Earth's Great Lakes, filled to great depth with all this liquid methane. And it really creates that kind of weather cycle just like we have on Earth, but just without the liquid water. And I should point out that the temperature on Titan is about minus 300 degrees Fahrenheit. So that is one key difference. But even so, we have, because of that methane cycle, all those similarities that I think will make Titan look a lot like you'd experience when you're flying across the surface of Earth in an airplane.
So why is our ultimate destination this Selk crater? What do we want to see there?
Well, we're first going to land in some sand dune areas because that's a safe place to land, and also because we have a lot of science questions about them. But you're right, the ultimate goal is to get to Selk crater, which is a really large crater on Titan. It's about 50 miles across, and we want to get there because we think that at Selk crater, the three ingredients you need for life were mixed together, and that mixing is very important because when that impactor came in, it created a lot of debris and mixed them all together. So we want to get Dragonfly to that crater so we have a chance to directly investigate what happens when you mix those three things together. Because the great thing about Titan is it's very similar chemically to Earth before life evolved. And we can't go back in time on Earth and learn the lessons about the chemistry that eventually led to life, but we can go to Titan and we can pursue those questions and look at that chemistry and get a glimpse into what those conditions were like that eventually led to life on Earth.
So Selk is kind of the holy grail, but it's got more than 24 flights before it gets there. So there's a whole variety of things it's going to be getting. What are some of the other samples and things that all these great instruments are going to be taking?
We'll spend a lot of time first going over those sand dunes, which are similar to some of the dunes that you see in the Namib area in Africa on Earth. They're rather tall. They're 100, 200 meters tall. There's a few miles between each of those dunes. So what we'll do is we'll actually fly Dragonfly over 1 or 2 or 3 of those dunes. We'll land in a smooth, flat area between them. And that's when we can do our analyses to try to understand what are those sands made of. Are they composed of those organics that drift down from the atmosphere? Have they been modified in some way? Have they been blown for long distances? And I think that'll be a very exciting part of the mission.
So why do we call Titan an ocean world? What does that mean? And I know there's several that we call ocean worlds. How does it compare?
Yeah, ocean worlds are a really exciting development in planetary science over the past 10 or 15 years. Earth is, of course, an ocean world because we have an ocean at the surface. But on worlds beyond Earth that lack atmospheres, you don't see oceans on the surface. You typically see them below the surface, like on Europa. What we're seeing with worlds like Titan and with Enceladus is they also have oceans below their surface. In Titan's case, perhaps 100 miles below the surface. And that has great implications for life because liquid water is one of the ingredients for life as we know it. And what Dragonfly will do is let us know if that ocean is close enough to the surface to mix with all those complex organic molecules that are falling out of the atmosphere. And if so, that means that we have more ingredients that are mixing together that could lead to life.
Well, thanks a lot, Kurt. We're starting to get a lot of questions on social media, so we're going to turn to them. If you're just tuning in, just want to point out that we're talking about a mission to Titan, Saturn's moon, that NASA has just selected today and announced. And if you want to ask a question, use the hashtag AskNASA on Facebook or Twitter, or leave a comment on whatever platform you're watching this on. So from Twitter, @TedCuriosity wants to know, what is the expected lifespan of Dragonfly?
That's a good question. Once we land, we will spend about 2.5 years flying around Titan. And we'll do, as you said, a couple dozen flights. And that will allow us to go about 180 kilometers so that we can get to Selk Crater.
C3LT Games wants to know, will Dragonfly have wheels or tracks, or does it only have propellers?
It only has propellers. It has skids underneath so that we can land on those skids. But anytime we want to move, we'll be using those propellers to fly. Some of those flights will be, 8 or 9 miles long, but it could be that once we land, we decide we just want to move 10 feet in that direction or 50 feet in that direction, and we can do that as well. And that's the great beauty of Dragonflies, because what we've learned when we go to other worlds is if you can move around, if you have mobility, you can learn a lot more, because there's nothing more frustrating than spending a year or 10 years trying to get somewhere, and you land and you realize, oh, I wish we were 10 feet over in that direction. Dragonfly can make that come true.
Wow. YouTube is with us, and Aura Master wants to know what rocket is going to be used to send Dragonfly to Titan.
That's a good question. And once we get closer to the launch date, we will actually take a look at what kind of performance we need, and then we will go ahead and look at what rockets are available and make a final selection. But we don't do that till we're about 3 years from the launch date.
And it's a long flight. It's like going to be about 8 years, and we're going to use a gravity assist. Is that right?
Yeah, we're going to launch in 2026, and we'll get there in 2024. I'm sorry, 2034. So it is a long flight, and that's the curse of exploration in the outer solar system. It always takes a long time to get there. But we will do a gravity assist of Earth, so once Dragonfly leaves, it'll come back for one final goodbye before it heads out to Titan.
We've got one more question right now from @Jeffrey on Twitter. Is Titan geologically active?
That is a great question, and that is something that we're debating quite a bit. It's geologically active in the sense that that methane cycle in the rain is carving new rivers, it's collecting in lakes. And one of the questions we've been debating is, are there cryovolcanoes on Titan? And what I mean by cryovolcanoes, instead of erupting lava, molten rock, on places like Titan where it's so cold, the lava is replaced by liquid water. Because when you're at minus 300 degrees, water ice is like granite. And when you have a cryovolcano, that water ice gets melted and behaves like lava. And we've had a lot of debates whether or not Cassini has seen evidence of cryovolcanoes on Titan. And it's still an open debate. But what we're hoping is Dragonfly, when it gets closer to South Crater, will actually be able to sample some of those cryolavas from the impact and see how that liquid water is mixed with the surface materials.
Wow, this is going to be a great mission. We're going to take more questions later in the show, so keep sending them at hashtag AskNASA. But right now, we're going to go to the Applied Physics Laboratory in Laurel, Maryland, which is the home institution of our principal investigator of Dragonfly. And Sophia Roberts is going to start talking to her, and we're going to find out a lot more about the actual spacecraft. Here you go, Sophia.
Thank you, Gray. Yeah, we are at Johns Hopkins Applied Physics Lab, and I'm here with the principal investigator, Zibby. Thank you for bringing us here to the birthplace of this amazing mission.
Thank you, our pleasure.
Oh, and I'm sure you're so excited, just having found out yesterday that this is going to be the next New Frontiers mission.
We're absolutely thrilled and ready to jump on in and get going to go to Titan.
All right, so now we can talk about the hardware of this. This is a 1/4 scale model of Dragonfly, right?
Yes.
So let's describe actually what size this is here.
Absolutely. So this is a 1/4 scale model. So Dragonfly is the size of a Mars rover. It stands about this high, and it's about 10 feet long. So we're used to drones that are small things that we fly around in our backyards. Dragonfly is really a Mars rover-sized drone that will be able to fly from place to place on Titan.
Wonderful. And what are you hoping to get out of this mission? What's sort of the end goal?
Well, Titan is just a perfect chemical laboratory to understand prebiotic chemistry, the chemistry that occurred before chemistry took the step to biology. We know that Titan has rich organic material, very complex organic material on the surface. There's energy in the form of sunlight, and that's what drives this really complicated chemistry in the atmosphere. And we know there's been liquid water on the surface in the past. And so these ingredients that we know are necessary for the development of life as we know it are sitting on the surface of Titan. They've been doing chemistry experiments basically for hundreds of millions of years. And Dragonfly is designed to go pick up the results of those experiments and study them.
All right, let's take a tour of what we've got here. Can you just show us what we're looking at?
Absolutely. So, so this is the 1/4 scale model of Dragonfly. Most of the instruments, because Titan is very cold, most of the instruments are actually inside the body of the lander, protected from the environment. You can see here, for example, there are a couple of windows. This is where our forward-looking cameras look out. There are windows underneath where we have downward-looking cameras because we'll be able to take images on the surface as well as in flight. We have up here, this is the high gain antenna. This is how we communicate, how we'll send data directly from the surface of Titan back to us on Earth. And these two boxes here on the high gain antenna are two more cameras, because the antenna allows us to move those cameras around. The antenna is designed to be able to move, to point toward Earth so we can communicate. And that means that we can use these cameras on the high gain antenna to point around to take a panorama of the terrain surrounding the lander at the different landing sites. The features here on the skids, we have two drills. There's a drill on each side. You can see the drill here behind a cowling. Because Dragonfly flies, we're not used to having to do this for space flight, but because Dragonfly flies, we actually have to think about aerodynamics. And so we've got protection to make sure that we don't have a lot of drag when we're flying. And these two drills feed a pneumatic system, basically like a vacuum cleaner, that they can drill down into the surface, and there's we can suck the material up into the mass spectrometer to measure its composition. So the mass spectrometer sits here inside the lander. And then there's another way we can measure the compositions of surface materials, and that's the gamma ray and neutron spectrometer. And with that, we can actually measure the composition of the materials surrounding and underneath the lander. So we get very high, very fine measurements of the chemistry at very local landing sites, and then at the very local sampling sites. And then we also get the bigger picture of the chemistry around the lander and underneath. And we can actually sense down to a few tens of centimeters that way.
So this is a machine that's going to sort of pulse, send a little pulse of energy.
Yes, so usually when we have gamma ray neutron spectrometers in flight, we can use the cosmic rays as sources, but the atmosphere of Titan shields us from that. So we actually have to bring a neutron generator with us to send out the neutrons so that we can receive the information back from the subsurface to be able to sense the different materials in the subsurface.
All right, I'm looking at this here, and I think it's so unusual that we were able to have a flying device here. So can you talk a little bit why we have, what, 8 rotors on this? Why did you choose to fly instead of roll?
Yes, so flying on Titan is actually easier than flying on Earth. The atmosphere is 4 times denser at the surface than the atmosphere at the surface of Earth. And the gravity is about 1/7 the gravity here on Earth. So it's actually easier to fly on Titan. If you put on wings, you'd be able to fly on Titan. So it's the best way to travel, and it's the best way to go long distances so that we can make measurements in a variety of different geologic environments. And that's what we want to be able to do, to understand how the materials on the surface have interacted in different ways.
Wonderful. So much more science, which is all that we want, right?
Absolutely.
All right, let's take a look again back here, because we've got some more parts perhaps behind here. What are we looking at right
so this is, Dragonfly is designed to use an MMRTG, that's a multi-mission radioisotope thermal electric generator. It's the same kind of power system that the Mars Curiosity rover is using. And so we use this to charge a battery, and then all of our activities are performed off of that battery. So when we fly, we fly off the battery, and then when we land, we can recharge from the MMRTG, simply because there's not enough sunlight that gets to the surface of Titan that far out in the solar system to be able to do solar power.
Is there something that you are really eager to tell the public about this mission?
The thing, well, there's so many things. There's so many things. One of the things that is particularly exciting about this mission is that we can do the very detailed chemical measurements, but be able to put them in the context of Titan as a system, so that we understand the way the materials interact, the way they have been mixed together. We have, in addition to the cameras and the instruments that measure the composition of Titan, we also have a meteorology suite. So we can measure the atmosphere, understand how the atmosphere changes day to day, for example. And we have a seismometer, and that will let us listen for Titan quakes to understand if the level of seismic activity on Titan, and potentially to measure the thickness of the ice shell over the deep interior liquid water ocean.
You know, the way all of you on this mission are talking about this, it sounds so much like we're talking about a planet, but just to remind all of you, this is a moon we're speaking about, which is incredible. I mean, it's got rivers, it's got an atmosphere, and it's still just orbiting Saturn, which, I mean, how wonderful is that to be going out there?
Absolutely. Titan is a very Earth-like place, despite the fact that the materials are very different at this very low temperature, and the bedrock is water ice, and the sand dunes are made of organic sand grains, and the liquid water, or the liquid on the surface, is liquid methane, despite the fact that these are very different materials than we're used to. The environment that they have made, that they've created on Titan, is incredibly Earth-like, and it has a very familiar feel.
All right, let's talk really briefly about that environment. What is it landing into? What does that look like?
So Dragonfly, the initial landing site is in the equatorial dunes. Titan has these vast sand seas, basically the largest Zen gardens in the solar system, wrap around almost the entire equatorial region on Titan. And so Dragonfly will land within these dunes in the interdune regions, and Although the materials are very different, this is actually very similar to some of the regions that we have here on Earth. So there's a very good analog for the Titan longitudinal dunes that we'll be visiting in the Namib Desert, where we have dunes that are very similar, except they're made of silicate and a lot warmer.
All right, I think it's about time to go for some questions with Ask NASA. So if you guys have questions out there, please use that hashtag #AskNASA and put it in the comment wherever you're watching or on Twitter. So I'm going to go take a look at what we've got going here. So Tom83 on Twitter is asking, are we going to be able to get high quality pictures?
Yes, we'll have a suite of cameras that will take images at different resolutions. We'll be able to take images of the entire landing site, the entire surrounding of the lander. We'll have the ability to image forward and downward. And then we have very high resolution cameras underneath the lander that will image the, I'll turn it a bit, that will image the actual site where we're sampling at very high resolution. And so we'll be able to get the context at different scales with the camera system. One of the things that's really fun, because we have dunes on Titan, one of the things we really want to study is the way the sands move. How much wind do you need for the sands to move on Titan, for example? And we don't need to wait for there to be a breeze. We can actually turn a rotor and do an active experiment with the sand that we're landed on.
Just
and
one rotor at a time?
Exactly, exactly. And then we can use the cameras to look down at that area and watch and see how much it took to make the sand move. And that will help us really understand the transport of these organic materials across Titan.
I'm so excited to see these pictures come back. Too bad it's a few years away.
We have to wait a little bit. We have to be patient.
All right, so from Periscope, we have Cyril Lampart asking, is there a fixed flight plan and key areas of exploration, and what do you expect?
Yeah, so Cassini has done a lot of work for us to scout the area that we'll be landing in. We initially land in the sand dunes so that we have access to this very rich organic material in the sand dunes themselves and the sand particles themselves. And then we will traverse over the ejecta blanket of the impact crater and down into the impact crater. So we have information from Cassini at the high level about the nature of the surface and what we may encounter. But what we want to be able to do, of course, is explore that at high resolution in situ at a much more human scale.
All right. So Jeff Polk on YouTube is asking, will methane rain on Titan pose any threat?
So we have thoroughly tested the system to make sure that is not a threat in terms of the flight system. At this time in Titan's year, we don't actually expect rain at the low latitudes. Titan's year is, because Titan has because the Saturn system has an axial tilt similar to Earth's, Titan has very similar seasons. And so in northern winter, the North Pole is unilluminated by the sun, the same way we have here on Earth, except that Titan's year is 29.5 years long. But because Cassini was able to observe 13 years of in the Saturnian system, it's almost half a Titan year. And so we know how the weather patterns changed seasonally. And because we're going to be landing basically one Titan year after the Huygens probe descended, at a similar latitude, we know what the atmosphere is like, and that it's that at that time of year, the weather systems are actually at the South Pole.
All right, Lily Carr, too, is asking, will Dragonfly be able to transmit video?
Well, we'll take a series of images. We can put those together as a series of images, but it won't be the same kind of high, HD TV that we might want to be able to see, because we're transmitting directly from the surface of Titan to Earth. But we will be able to put together a series of images in a sequence.
All right, that'll be good enough, I guess.
We'll be getting images from the surface of Titan. It'll be good.
From Twitter, we have @Mr. Coggle is asking, can Dragonfly land on hills or mountainous areas?
So Dragonfly is designed to fly autonomously. and to land autonomously. And so we have a hazard navigation system. Some of the windows here are part of that navigation system. And so we would be able to detect slopes that are too steep, for example, to land on, and then navigate to a flatter landing site. So we can land on some degree of slope, but we can make sure that we always find an area that is a lower slope to land on.
All right, and the Guy Man on YouTube is asking, who manages this mission?
The mission is managed by the Johns Hopkins Applied Physics Laboratory here in Maryland.
All right, and then from Periscope, Corey J. Turner is asking, is this a final design, or will it be tweaked before the launch in 2026?
Yes, so what we've done is the initial mission concept. We've demonstrated that the concept closes, as we say, that the design is robust to the environment that we understand. As we move forward with the development of the mission, there will absolutely be design tweaks, modifications, as we start to build the different units together. The fundamental design of Dragonfly, we would expect to stay very much the same, but there will absolutely be modifications, perhaps a little more aerodynamic shape, for example. I think the rotorcraft team would appreciate that.
Well, we're all sitting on our seats excited about this. And before we go off to our next section, I just want to remind you that here in this front area, we have the mass spectrometer. And I hear that we have a great model of that back in the studio. So Gray, take it away. Thank you.
Thank you.
Thanks, ladies. So as Zibby mentioned, the model she was just showing you was a 1/4 scale model. The actual vehicle is much larger. What you see here is a full-scale model of that mass spectrometer that sits at the front nose of Dragonfly. And it's in a place called the attic, so it's at the top. You heard us talk about how cold Titan is, and we keep all the electronics inside Dragonfly so we can keep them warm, except for this area up here, which I'll talk about. But the mass spectrometer is there so we can get compositional data to tell us what the surface of Titan is built of. And this is an incredibly complicated and powerful instrument. And it gives you an idea of how large the Dragonfly spacecraft is overall, because this fills the entire nose of it. So what we do when we take a sample, as Zibby said, we have drills down on the skids of Dragonfly. And what those drills do is create a sample, and then we suck it through some tubes just like a vacuum cleaner does. And it gets sucked up here to the front into this round area, which is a sample carousel. And what the sample carousel has is a bunch of different cells here. These tubes are each different sample cells. There's 48 of them. So that sample is delivered into these tubes, and then we can take two different measurements. There's one type of mass spectroscopy measurement that is taken right here, and then the second one is taken here. And this is actually a miniature oven, because what we do with that sample, that ground up dirt or sand, if you will, is for the second measurement, we actually bake it. We heat it up so that it gives off gases. And then the gas chromatograph that is behind here measures the composition of those gases. And when we use both of those measurement techniques, it gives us a tremendous amount of information about the composition of the sample, about those complex organic materials that we were talking about, and also can look for signs of life.
Thanks a lot, Kurt. It's not every day you get to see a life-size model of an instrument that's going to fly halfway across the solar system. If you're just tuning in, we are talking about Saturn's moon Titan, where we're going to fly. It's NASA's newest mission in the New Frontiers program. And with us is Dr. Kurt Niebuhr, and we also have another team member with us now. Lene Quick is the head of the Science Enhancement Opportunities part of the mission, and that's kind of about getting the new STEM leaders of tomorrow involved in Dragonfly. Dragonfly is really a mission about the future, and so tell us a little bit more about what that is.
Yeah, so we have the student enhancement option, which is a unique opportunity to get students involved in Dragonfly science. And what we'd like to do is we'd like to have students come and scientists and engineers and work on the Dragonfly mission throughout the entire life cycle of the mission. So from phase B onward, we hope to have students get experience in real time working on missions, and let that be something that they can tap into for later in their careers.
So yeah, you kind of answered it a little bit, but why is SOE, as we call it, why is it important?
So SOE is very important because what we want to do is we want to train the next generation of planetary scientists while also broadening the STEM pipeline, and the SOE is the perfect model to do that. What we'll be doing is just bring in students from a broad swath of fields, physics, chemistry, biology. I think when Kurt and Zibby talked about the interesting science that you could do at Titan, you know, it's a laboratory and it's a grab bag of different things you can do, and there are so many different disciplines that could come and make a great contribution to our science. And one thing that we also talked about earlier was that Dragonfly will not be launching until 2026, and then it'll reach Titan in 2034. And by that time, a lot of us who are on the mission now will be mid-career or will be late career, and really what we want to do is train people who can come and who can take over and kind of take up the reins as far as leadership on our mission, and not only on Dragonfly but on other missions in NASA's planetary science portfolio in the future.
So you're a scientist.
Yes.
I imagine this would have interested you early in your career.
It would have definitely interested me early in my career. I was, my bachelor's degree is in physics, and so I didn't think about planetary science or how what I was learning as a physics major could be applied to, you know, obtaining a PhD in planetary science until much later. And if there was a program similar to the science enhancement option when I was in college, it would definitely have been something that would have opened my eyes to planetary science and planetary geology as an exciting field much earlier.
Well, thanks a lot, Lene.
Thank you.
Obviously, this is just a really new announcement, Dragonfly, so we're still getting up and running. There'll be a lot more materials online in the future, so please feel free to check back at nasa.gov, and eventually you can connect with Lene and find out more about how you could get involved with Dragonfly. So we're going to go to some more questions from social media. Again, that's Ask NASA. Use that hashtag on Facebook or Twitter or in the comments box of wherever you're watching this from. And again, if you're just tuning in, we're talking about a really exciting new NASA mission to the moon Titan of Saturn. David on YouTube wants to know, I think this will be one for you, Kurt, how you make sure Dragonfly won't bring living organisms like bacteria and contaminate Titan.
That's something that NASA takes very seriously. We call it planetary protection. And we want to be sure of two things. First, that we don't contaminate what we're going there to study. And second of all, we want to make sure that the measurements we take are not contaminated by what we bring along, because we're going there to learn about Titan. We're not going there to learn about the stuff we took along with us to Titan. So we have processes and techniques we use that clean all of our spacecraft that go to places like Titan, where we're going to be measuring organics or perhaps looking for life. So we make sure the spacecraft are very clean. Sometimes we bake them at high temperatures to kill off anything that we might take along with us. And in the case of Titan, it's not as concerning because we know that once we land, as I mentioned, it's minus 300 degrees. Anything we bring along that's alive is going to freeze really quickly. So even if our cleaning processes fail, we have that to fall back on.
Now, we've been talking a lot about methane the last couple weeks on Mars and now on Titan. Ayush Capri on Periscope wants to know, what's the difference between methane in Titan versus what we would find on Mars?
Well, I think the big difference is there's a lot of methane on Titan. And what we're seeing at Mars is very small amounts, and they're still trying to understand what those measurements mean and how they vary through time. But the methane that we're seeing on Titan is very much a natural process. It's being given off into the atmosphere. But the interesting thing is that methane should not stick around. It should break apart. And so something is replenishing it. And one of the things we want to try to understand, and what Dragonfly will help us understand, is what is renewing that methane? What is the source of all that methane? And we think it's geologic in nature, not biologic. But again, that methane as an organic compound can have a role in the pre-biologic processes that we're going to methane to investigate.
Fascinating. Got one for you, Lene. At Guigo Soldadino on Twitter wants to know, can students from around the world work on the Dragonfly project?
Oh, can students from around the world work on the Dragonfly project. I'm sure that we will find a way to allow as many people who are interested in working on this project to work with us, of course, with going along with whatever NASA wants us to do. But we're very excited to have students from all different backgrounds work with us on this mission.
Great, thanks, Lene. Yeah, a lot of details still to be worked out, but definitely something to get excited about. Oh, here's an interesting one. For you, Kurt, Orange Builder on YouTube wants to know, will we see images of Saturn in the titanium sky?
Oh, that's a good question. And to be honest with you, I don't know, Lene. Can you see enough of Saturn through the clouds and the thick, hazy atmosphere?
I'm not sure that you can. I think you may be able to see just maybe a faint trace, but I don't think that we'll be able to see much of Saturn at all through the clouds.
I think that stay tuned until 2034.
That's right.
Scott on YouTube wants to know, is there a limit on Dragonfly's flight?
Well, the ultimate limit is going to be the MMRTG, the nuclear power source, because as Zibby said, that's what charges up the battery. But fortunately, the way they have designed this mission, it'll be about 8 years after we land on Titan that it gets to the point that that nuclear power source stops providing enough energy for Dragonfly to survive the cold environment. So that's the long limit. But beyond that, you simply need to worry about different parts or motors wearing out. And fortunately, we're used to that kind of thing at NASA. We understand how to design things that need to last for how long they need to last. And I think the great example of that is the Mars rover Spirit and Opportunity. We needed them to last for 90 days of operation on Mars. They lasted for over a decade.
So here's a good one from Kinetics SNAFD on Twitter. How long is it going to take Dragonfly to downlink an image from the surface of Titan to Earth?
That's an interesting question. As Zibby said, we have that really large high gain antenna, and it is about yay big across. And we'll be using that not when we're flying, only when we're landed. But I'm not sure what the data rates are going to be. It'll probably take several minutes of downlink time to get each image, and that's one of the reasons Zibby said we're not going to have movies, high-def movies, while we're flying, but we will have enough bandwidth that we can send back successive images, pretty high-quality images, that are taken while we're in flight, and then you can stitch those together into a movie.
Well, we really appreciate both of you guys' time today. That's all we have time for right now as far as questions, but this is not the end. There is a Reddit AMA on Monday at 3 p.m., so if you want to come back and ask some more questions of Kurt and some other folks as well, please do that. I'm just going to go with one more question with each of you guys, same one. What are you most excited about Dragonfly?
What am I most excited about? Well, I feel like Kurt set me up for this one by talking about cryovolcanoes, so I'll just go back to that one. In my work, I model just the eruptions of these icy fluids or this slush onto the surfaces of ocean worlds, and I'm used to thinking about worlds like Europa, where we have this slush that erupts, and it's very young, and there's nothing to bother it because there's no atmosphere and there's no weather. But when we think about Titan, that's a different situation. We'll have fluids that may erupt onto the surface, and they may, so we may have young surface areas that have been eroded and weathered, and that's something that I really haven't really thought too much about, but I'm excited to have to think about it now. So, yeah, very excited about that.
That's cool.
Yeah.
Yeah. What do you, Kurt?
I think for me, just as you mentioned, Gray, just the idea that we're going to be flying over an alien world that's circling another planet is mind-boggling to me. And I think as we're skimming across the dunes, the pictures we get back from in flight are going to be unbelievable. But I think the real thing that will take our breath away is as we're getting closer and closer to South Crater, and we see that fill the image and get bigger and bigger and bigger as we get closer and closer. I think that is going to excite the entire planet.
I think you're right about that, Kurt. This is it for today, but as I said, this is just the beginning. This is going to be a great mission, and a lot of people around the world are going to have chances to be involved with it for many years to come. So again, if you didn't hear me, there is an Reddit AMA on Monday at 3 p.m., so please join us for that. There's a lot more questions, and we look forward to talking to you all. And go Dragonfly!